Of all the ideas in calculus, the integral is the one that captures the simplest question you can ask about a curve. How much is there? How much area lies underneath? Pick a function, and a window from A to B. Slice that window into thin vertical strips. Each strip is almost a rectangle, with height f of x and width delta x. Add up all the rectangles, and you get an approximation of the area. Now let the strips become infinitely thin. In the limit, the sum becomes the definite integral of f from A to B, written with that elongated s, a reminder that integration is, at heart, a sum. Here is the miracle that makes calculus work. Differentiation and integration are inverse operations. If capital F is an antiderivative of f, meaning its derivative equals f, then the definite integral of f from A to B is simply f of b minus f of a. This is the fundamental theorem of calculus. A question about area becomes a question about antiderivatives. To evaluate an integral, we have two main tools. Substitution reverses the chain rule. If u equals g of x, then du equals g prime of x dx, and the integral transforms into a simpler one, and u integration by parts reverses the product rule. The integral of u dv equals uv minus the integral of v du. Armed with these two tricks, a huge range of integrals becomes tractable. And then there are the integrals that feel like magic. The Gaussian, e to the minus x squared, has no antiderivative in elementary functions. And yet, its integral over the entire real line is exactly the square root of pi. The proof is beautiful. Square the integral, convert to polar coordinates, and the impossible collapses into something you can evaluate by hand. A curve shaped like a bell, tied forever to the geometry of the circle. Integrals are how we turn slicing into summing, and summing into answers about area, probability, and motion. One symbol, infinite applications.